Welcome to the Greater Essex County District School Board calendar, where we will be focusing each month on the fundamentals of mathematics. Each month, we will be diving into a big idea from the Ministry of Education's Focusing on the Fundamentals of Math, a teacher's guide, and in particular, the table that summarizes the fundamentals of mathematics from the current Ontario math curriculum into different categories. This month, we'll dive into working with numbers, and in particular, magnitude of whole numbers. When you think about magnitude, what we're referencing is the how muchness of numbers that we use to measure quantities. So let's go ahead and start with an example that might help reference the importance of magnitude. We're going to start with an idea that was shared originally on Twitter by Mark Chubb, a math coach from Ontario, to help us unpack some ideas related to magnitude. So let's start with a number line. We'll just put a 0 over here like you'd probably expect. However, we're going to do something you might not expect. Instead of putting a number like 10, 100, or even 1,000 on the other end of this number line, I'm going to put 1 trillion. That's right, 1 trillion. The reason I'm doing this is to share just how important the idea of magnitude of number really is for all of us, but especially our students. And what I'm going to have you do is take a moment to think about where you imagine 1 billion going on that number line. Go ahead, take a little time, maybe even pause the video to visually place where you would put 1 billion on the number line, or even draw it out. So, what do you think? Do you think that a billion would go somewhere around here? Well, that would mean that 1 billion is half of 1 trillion. How about somewhere around here? Now, this might seem more reasonable. However, that would mean that 1 billion is 1/4 of 1 trillion. And that's not quite accurate either. How about here? Nope. When we really think about it, 1 billion is 1/1000th of a trillion. In other words, there are 1,000 billions in 1 trillion. Did you think that 1 billion would be this close to zero? I know that initially I wasn't thinking about it that way myself, and that's because I wasn't thinking about the magnitude of the numbers comparatively to one another. Now you might be wondering to yourself, why does the magnitude of number matter anyway? Well, research tells us that increasing reliance on linear representations of number, just like that number line we used just a moment ago, plays a central role in the development of numerical knowledge. And in fact, Kathy Fosno, an educator and researcher of how children learn mathematics, goes on to explain that developing our understanding of magnitude of number using linear number line models correlates positively with accuracy of magnitude comparison, like when students must determine how much more or how much less one quantity is than another, or figuring out answers to unfamiliar addition problems, and overall math achievement test scores. Now, as I'm sure you'd agree, there's something to this idea of magnitude, and using linear models is a helpful way to help students build that understanding. So, we already gave a pretty extreme example to possibly highlight our own limited understanding of magnitude as numbers get quite large, like billions and trillions. Let's take some time to think about what this might look like for our youngest learners who are just learning how to count. We need to keep in mind that just because a child can count to 10, 20, or even 100, that doesn't necessarily mean that they have an understanding of magnitude. So we're going to begin with one of the most accessible linear models for our youngest learners that we typically call a number path. Now, it might be helpful early on to leave some space between the squares so that children can feel as though they are counting a set, but over time, removing that space can be helpful to also make measurements. Now, if I was to cover this number path up with this bar, we still know there are 10 squares underneath. A good way to develop student understanding of magnitude would be to ask students where about do they think the number 2 or the second square would go. We could then ask them to tell a neighbor or their siblings if you're at home while you're doing this. Ask them to point on the screen or on the paper if you've cut these out to get a sense of their understanding of magnitude. You could also lead them to attempt identifying by color where the number 2 should go. And we can continue asking them to indicate by describing or pointing on the bar where the other numbers go relative to the first square, which they know is 1, and the last square that they know is 10. So for example, if we asked where 8 goes on this bar, students could then try to point on the bar whereabouts do they think the number 8 should go. Now, as you can imagine, as children continue practicing this, they will not only be developing a sense of magnitude of number, but also developing their overall number fluency. Over time, as we scaffold student thinking from a concrete linear path using objects themselves, connecting cubes, square tiles, or other manipulatives, to pictorial number paths, just like what you see drawn or created up on the screen, we can then finally start moving on to something a little more abstract, but very helpful to us, and it's this idea or this thing, this model we call the number line. Something to note is that making a shift from a number path to a number line introduces the challenge of asking students to think more abstractly. First of all, instead of counting individual objects, like you can with objects in a set, connecting cubes, square tiles, or squares on the screen, students are forced to count the spaces between the hash marks or the ticks on a line, which proves to be very challenging for young learners. They are now also introduced to this idea of 0 or nothing very explicitly, whereas in the past, if there was 0, there was nothing there to see. So as students build their understanding of magnitude and ability to think more abstractly, they can begin to use jumps on the number line as a way to solve addition, subtraction, and even multiplication and division problems. As their understanding of magnitude deepens, we can continue pushing their range to larger quantities to ask questions like, where does 72 go on this number line from 0 to 100? While a variety of strategies could be helpful here, some students might attempt finding the midpoint between 0 and 100, which they may know is 50. Then they might half again, but this time the distance between 0 and 50 to reveal where 25 should lie. And from here, they might use their understanding of fourths of 100 cents or $1 to determine that the 3/4 mark, or halfway between 50 and 100, should be 75, leaving the students to place 72 a tad to the left of 75. And then we can stretch out even further and now utilize a very similar strategy, noting that since the number line is 10 times bigger, or at the magnitude of the values on this number line are 10 times bigger, and the number I want to place is 10 times bigger, the same partition should work, placing 500 at the halfway point, 250 at the fourth or the quarter mark, and 750 at the 3/4 or 3/4 mark of the line. And the same is true when we scale our quantities up by another factor of 10. And we can continue doing this until we are at quite large quantities, even numbers as high as 1 billion, or even 1 trillion. So when we ask a question like, where does 720 billions go on this number line? This problem is much easier to handle. So next time you're grappling with numbers that just seem too large, remember to think of the importance of magnitude and try to visualize the quantities you're working with linearly. Then, even seemingly challenging problems will be accessible. Be sure to join us in the next video where we'll extend our understanding from magnitude to place value. We'll see you then.